Assalamualaikum and welcome. Today we're going to present about PT-100 sensor configuration for accurate temperature measurement in insulated environments. Our group members are Najiha, Uzma, Siti, Syazwina and Nabilah, Husna.
So the objective of this experiment is to evaluate the accuracy of PT-100 sensors in different configuration using an insulated flask with dry ice. Next, to determine the thermal resistance and also the response time of each PT-100 sensors configuration in a stable temperature environment. So lastly, our objective is to identify the most suitable PT-100 sensors configuration for precise temperature measurement under varying thermal contact and also insulation condition. Next, we proceed with the methodology. Firstly, an insulating flask was filled with dry ice to create a controlled environment. 3 PT-100 sensors were then placed into the flask under different conditions, which is the first sensor was placed directly in contact with the dry ice. Another sensor was placed inside a tube as a unit under test UUT, and the third sensor served as a reference standard. Each of these PT-100 sensors were connected to a precision digital temperature indicator. The temperature readings were monitored and also recorded every 20 seconds, allowing sufficient time for the dry ice to stabilize with the surrounding temperature. The primary objective was to evaluate the performance and accuracy of each sensor configuration by comparing their reading against the reference standard. If the reading exhibit rapid temperature changes or high thermal resistance, those configurations were deemed less accurate. The configuration that provided the most consistent and accurate readings, closest to the reference standard, was identified as the best setup for precise temperature measurement. So this process helped to determine the optimal PT-100 sensors configuration for reliable and precise temperature measurement under varying thermal conditions.
And for the results and analysis part, we measured the type of standard, direct, and UUT inside a tube. These three types were measured with the time represents the y-axis and the temperature represents the x-axis. For the time, we measured 0 second until 20 seconds, and at graph, the figure at the right side was about the temperature versus time. At the upper side was referred to the reference standard, and the right one was represents to the direct, and the last one was represents to the tube, which is UUT. And this figure were about the temperature profiles of PT-100 sensors in different configurations over time.
Moving on next to the discussion part. The reference standard configuration needed recorded the lowest temperature. This is due to its low thermal resistance and efficient heat transfer, making it the most accurate and consistent in temperature readings. We use this configuration as our baseline for comparison. Next, when the PT-100 sensor was in direct contact with dry ice, it displayed slightly higher temperature, indicating moderate thermal resistance. On the other hand, the tube UUT arrangement showed the highest temperature. This suggests that the tube provides significant thermal resistance, affecting the sensor's reading. The tube configuration is particularly beneficial for environments that require sensor protection from harsh conditions or rapid temperature changes. However, the comes with a trade of it results in slower response times and higher temperature readings. Lastly, our results highlight the importance of selecting the right sensor configuration based on the specific demands of your application. Consider factors such as accuracy, response time, and environmental protection to ensure optimal performance.
So in conclusion, we test PT-100 sensor in 3 configurations: reference standards, direct, and tube UUT, using dry ice-filled insulating flasks. The reference standard configuration provided the most stable and accurate measurements due to minimal thermal resistance. The direct configuration shows slightly higher temperatures, which we attribute to moderate thermal resistance. The tube UUT configurations exhibit the highest temperatures and slowest heat dissipations, indicating the highest thermal resistance among the 3. We observed that temperature accuracy was affected by sensor placement inconsistencies, contact quality variations, and environmental adaptability. To improve accuracy, it is essential to ensure uniform sensor placements, maintain consistent thermal contacts, and minimize external temperature variations. Regular calibration of PT-100 sensors is also crucial for precise measurements. Enhancing reliability can be achieved by securing consistent sensor placements, conducting experiments in controlled environments, and increasing measurement for better averaging. By addressing potential errors and implementing these suggested improvements, future experiments can achieve more accurate temperature measurement using PT-100 sensors in various configurations.